In my earlier video, I had discussed about some theorem based on Riemann integration. Today I will discuss this topic elaborately. Seen in my earlier video, when function defined from AB to R, when the function is continuous on the closed interval AB, then function is always Riemann integrable on the set AB. And when the function is monotone on the closed interval AB, then function also Riemann integrable AB. This I had seen in my earlier video elaborately. I had proved this. Every continuous function always Riemann integrable and every monotone function always Riemann integrable. Similarly, if a function defined from AB to R is Riemann integrable on the set closed AB, then obviously the function must be bounded on the set closed AB. But the converse is not true. When the function is Riemann integrable, then the function must be bounded. But if f is bounded, then that does not imply always f is Riemann integrable. As for example, seen in my earlier video, fx equal to 1 when x belongs to rational number and fx equal to 0 when x not belongs to rational number, this function not Riemann integrable. But this function is always bounded function. So, bounded function does not always imply the function is Riemann integrable. But every Riemann integrable function always will be bounded. I will see some property of Riemann integration. If f is Riemann integrable on the set closed AB and C be any scalar, then multiply the function with this scalar is always be Riemann integrable, and C times integration a to b fx dx always equal to integration a to b c fx dx. Okay, means the scalar which I have multiplied in this function can be taken outside of this function. Okay, this is one property. Second property, if f and g be the Riemann integrable on the set AB, then the new function f plus g always be Riemann integrable. Then integration a to b f plus gx dx always equal to integration a to b fx dx plus integration a to b gx dx. Third property is, if f and g be the Riemann integrable on the set AB and if fx less than equal to gx for all x belongs to closed AB, then integration a to b fx dx always less than equal to integration a to b gx dx. Fourth property, f is Riemann integrable on the set closed AB and if a less than c less than b, then f is Riemann integrable on the set AC, also f is Riemann integrable on the set CB. That means integration a to b fx dx always equal to integration a to c fx dx plus integration c to b fx dx. Fifth and last property is, f is Riemann integrable on the set closed AB, then absolute value of f obviously be Riemann integrable on the set AB, then absolute value of integration a to b fx dx always less than equal to integration a to b absolute value of fx dx. I will not prove this property because this type of proof is very boring. Just try to answer. This is very easy type proof but very lengthy type proof. But this type of property will use to find the Riemann integration of a function easily. Continuous function always imply Riemann integrable. But if a function not be continuous then this function will be Riemann integrable. Let's see. I will define one nice function. F is defined from closed interval 0, 1 to R. The function is defined as when x is irrational, then value of the function is 0, and when x be rational, then value of the function is 1 over q. And the graph is look like when the function irrational, then value is 0. When the function is p over q, then the value of the function is 1 over q. When the irrational, then obviously value 0. Consider 1 over 3, then the value of the function would be 1 over 3. If we take 1 over 2, then value of the function would be 1 over 2. If we take the point 2 over 3, then also value of the function is 1 over 3. And if you take 1 over 4, then also value of the function is 1 over 4. And otherwise, at the point irrational, the value of the function is 0. Here this function is like a popcorn. So this function is a popcorn function. Also this function had defined the mathematician Thomas. So actually this function is by the mathematician. This function is Thomas function. Are you getting? Well, I had defined this type of function in continuity lecture. I had seen this function is continuous only irrational point. Now I will see, is this function is Riemann integrable? Then consider this is the epsilon. Then how many points B exist above the epsilon? Here the set A equal to set of all x belongs to closed 0, 1 such that f of x greater than epsilon. When x not equal to 0, then f of x equal to 1 over q. That means we have to find 1 over q greater than epsilon. That implies q greater than 1 over epsilon. Then how many q are possible which is greater than 0 and less than 1 over epsilon? How many q possible? This is obviously finite. That implies the set A is finite. Actually, we have to find the set of points which is goes above this epsilon, and this would be obviously finite. As capital A is a finite set, consider 0 less than x1 less than x2 less than xn equal to 1. At those points, the value of the function is greater than epsilon. Since the point is finite, consider this is x1, this is xi, similarly this is xn. And since the point here the finite, we want to enclose each point by an interval, then obviously total length would be finite because the point here the finite. That means enclose these points in interval of total length small for all I, then find I an interval such that for all x belongs to the interval I, the length of this interval, sum of length of this interval I equal to 1 to n, length of this interval always would be small. Consider this is less than epsilon. This is just like a partition. Here the interval 0, 1 and this is x1, this is x2, this point is xi, this is xn. And consider the interval which I have enclosed each points. Consider this is A1, this is B1, this is A2, this is B2, this is AI, this is BI. Similarly, this is AN, this is BN. And here the point 0 and here the point 1. That means here A not equal to 0 and here AN plus 1 equal to 1. That means the partition is look like here 0 equal to A naught, less than A1, less than B1, less than A2, up to less than AN, less than BN, less than 1, and 1 is actually equal to N plus 1. Now consider the interval AIBI. The UPF would be summation I equal to 1 to N capital MI times length of the interval plus, here notice at first for this interval where the interval is look like AIBI, but if you consider this interval, this blue plot, then this would be for each blue interval to find the UPF. At first we have to find the maximum value of the function for each sub interval and the length of this interval, and this is actually would be summation j equal to 1 to n capital Mj times Aj minus Bj minus 1. Are you getting? J part is for this part and I part is for this part. Here notice with the maximum value for this interval. Since the function is bounded, that means this would be less than equal to capital M, some number capital M, obviously since the function is bounded, times summation I equal to n length of the interval, plus here the supremum of the function would be for here the set is such type of set where in this interval the value of the function is greater than epsilon. That means here those points where the value of the function is greater than epsilon, but here the point is finite. So for this part obviously Mj would be less than epsilon. That means this is less than epsilon times j equal to 1 to n Aj minus Bj minus 1. Are you getting? Consider it this part less than epsilon, so this would be less than capital M times epsilon plus epsilon times this would be always a finite number. Consider this is also M1, so this part would be less than epsilon times M plus M1. Therefore the main idea is I have got a partition where upper sum would be less than epsilon times some constant. Actually in analysis constant does not matter. Since LPF equal to 0, so UPF minus LPF obviously would be less than epsilon. That means obviously this function be Riemann integrable on the closed interval 0, 1. That means Thomas function always will be Riemann integrable. Are you getting? This is very interesting type of example. The proof is very interesting. Here I have considered such point when the functional value is greater than epsilon. Because when the functional value less than epsilon, then obviously the function would be less than epsilon, because here the LPF always equal to 0. So I have considered such point where the functional value greater than epsilon, and obviously this point are finite, and I have seen in this point also the difference between UPF and LPF less than epsilon is the function has discontinuity every rational number of point. So the function has a infinite number of discontinuity, but still the function is Riemann integrable. I will see one interesting example. Consider the function such that fx equal to 1 for x not equal to 1 and fx equal to 0 for x equal to 1. And consider the interval close 0 to. Prove that the function f is integrable. Consider this interval 0 to. Here at the point 1, notice for x equal to 1, the value of fx equal to 0 and otherwise the value is 1. See the graph. When x not equal to 1, then the value is 1. When x equal to 1, then the value of the function is 0. Notice. Now we have to prove the integrability UPF, which is equal to capital MK times length of each subinterval, and if we partition 0 to interval, then obviously for each subinterval the highest value of the function is 1, then MK would be 1 and length of each subinterval, and if we sum them, then this would be just 2. And this value would be 2. LPF, consider the partition 0, 1 minus epsilon over 3, 1 plus epsilon over 3, comma 2. That means here consider this partition for LPF. That means the lower sum would be for this partition k equal to, here only 3 partition, k equal to 1, 2, 3, small mk times xk minus 1. And here at all point the value of the function is 1. Only when x equal to 1, then the value of the function is 0. So when you will choose 1 minus epsilon over 3, this interval, then the value of the function is 1. So for this interval, the value would be 1 times 1 minus epsilon over 3 plus, and if we choose this subinterval, then at the point 1, the value of the function is 0. That means infimum of the function in this subinterval would be 0. Then for this subinterval, the value would be 0 times 2 epsilon over 3 plus for this subinterval also the functional value is 1. That means this would be 1 times 1 minus epsilon over 3. This value would be 2 minus 2 times epsilon over 3. Distance between UPF minus LPF would be 2 times epsilon over 3, and this is actually less than epsilon. So since UPF minus LPF less than epsilon, so obviously function is Riemann integrable on the closed interval 0 to. In this function has a discontinuity at the point 1, but still the function be integrable. It's a nice theorem. If a function f is bounded and has finitely many discontinuity on the closed interval ab, then obviously f is integrable. So one same type of question also. Fx equal to 0 when x not equal to half and 1 when x equal to half. Notice here discontinuity only at the point half, because at the point half the functional value is 1. Since the function is bounded and there exists one discontinuity, that means finite discontinuity. So by the theorem, obviously f is Riemann integrable on the interval 0, 1. And mathematically, if we want to find the Riemann integration of this function, then this would be, since the function has a discontinuity only at the point half. Consider a subinterval at the point half. Same like before example. Here the subinterval is look like 1 minus epsilon over 2 half 1 plus epsilon over 2. And since when x not equal to half, then everywhere the value of the function is 0. So LPF equal to 0, because for any partition P of the closed interval 0, 1 and any subinterval xk minus 1 to xk of the partition P, there is some x belongs to xk minus 1 to xk with fx equal to 0. Because everywhere only at the point half the value of the function is 0. So mk equal to 0. And since small mk equal to 0, that means LPF equal to 0. Are you getting? But only problem to find UPF, because at the point half the value of the function is 1. For this, for any partition P of closed 0, 1, UPF greater than equal to 0 for all x belongs to closed 0, 1. Let epsilon greater than 0. Then the partition is look like 0 less than 1 minus epsilon over 2 less than 1 plus epsilon over 2 less than 1. This is the partition of closed interval 0, 1. Then notice there are 3 sub-intervals similar to before, where f is only non-zero on the interval 1 minus epsilon over 2 to 1 plus epsilon over 2. Okay? Then UPF would be just k equal to 1 to 3 capital MK times xk minus 1. Since f is only non-zero on the subinterval this, then this value would, and at this point the maximum value of the function is 1. Now put the value, because otherwise the function is 0. Then this value would be epsilon. So for any epsilon belongs to open interval 0, 1, there is a partition P epsilon with UPF equal to epsilon. And since UPF is small epsilon, that means UPF equal to 0. Therefore, I have got LPF equal to 0 and UPF equal to 0. Since both 0, therefore the integral 0 to 1 fx dx would be 0. Are you getting? Oh well. The theorem is a bounded function f is Riemann integrable over the closed and bounded interval AB if it has infinite number of points of discontinuity and otherwise has finite number of limit points. If a function has infinite number of discontinuity or it has a finite number of limit point, then obviously this bounded function be Riemann integrable. Thomas function, here the discontinuity at the point rational number. So notice here the limit point of the discontinuity tends to 0. So this function be always Riemann integrable. Are you getting the theorem? Example. Consider fx equal to 1 when x equal to 1 over n and 0 when x not equal to 1 over n when n belongs to natural number. Now I will check, is this function is Riemann integrable on the closed interval 0, 1? This is just thing. This is 1, this is half, this is 1/3, this is 1/4, and this would be 1/5. At this point, the value of the function is 1, and otherwise here the value of the function would be 0. And notice here, when x equal to 1 over n, then the function has a discontinuity. That means this function has infinite number of discontinuity. And actually this is a sequence, and this sequence tends to 0. This function is bounded function on the closed interval 0, 1. That means since the function has an infinite discontinuity, but still the function is bounded, so obviously the function is Riemann integrable. As seen in my earlier video, gx equal to 1 when x belongs to q and 0 when x not belongs to q. This function is not integrable on the closed interval 0, 1. Because this function is obviously bounded function, but here the graph is look like when rational then value 1, when irrational then value 0. That means this function has everywhere discontinuity. So this function is not Riemann integrable, but this function has a discontinuity at infinite number of points, and this discontinuity converges to the point 0. So this function is integrable, but since this function is everywhere discontinuity, so this function is not integrable. Are you getting? Oh, here when x belongs to q, then the functional value is 1, and when x not belongs to q, then the functional value is 0. That means here the UPF equal to 1 and LPF equal to 0. So the function not Riemann integrable on the set 0, 1. Are you getting? I will see one nice example, step function. We all of us know step function. Consider the step function fx equal to box x is integrable on the set 0, 3. We all of us know the interval 0, 3. So step function is defined as 0 when 0 less than equal to x less than 1, and when 1 less than equal to x less than 2, then value is 1, and when 2 less than equal to x less than 3, then value is 2, and when n greater than equal to 3, then the value would be n. We all of us know this is the step function, and here in the interval 0 to 3, fx lies between 0 to 3. So fx is bounded on the closed interval 0, 3. And this is the graph. At the point 0 to 1, the value of the function is 0. At the point 1 to 2, the value of the function is 1. At the point 2 to 3, the value of the function is 2. Here notice, at the closed interval 0, 3, the function has a discontinuity only at the point 1 and at the point 2. Because here the function is constant function. Also here constant function. Only discontinuity at the point 1 and 2. So, since the function is bounded and has a finite number of discontinuity, so obviously the function is Riemann integrable. Are you getting? Otherwise, other method, we all of us know, every monotone function is a Riemann integrable. Here notice, since this is constant function, so this function is obviously monotone function on the interval close 0, 3. So obviously this function is integrable on the interval 0, 3. Are you getting why the property of Riemann integrable is more important to find the Riemann integration? Here you can use, if a function is bounded but has a finite number of discontinuity, then function is Riemann integrable. Also you can use, since the function is monotone function on the closed interval 0 to 1, then function is integrable. Okay. If you want to find the integration 0 to 3 box x dx, then this would be just divide at the point at first 0 to 1 box x dx, then 1 to 2 box x dx, then 2 to 3 box x dx. Are you getting? And 0 to 1 the functional value is 0, and 1 to 2 the functional value is 1, and 2 to 3 the functional value is 2. And if you want to integrate of this part, then this would be 0 plus here x 1 to 2 plus 2x here 2 to 3, then this value would be 3. Are you getting why I have told you the property of Riemann integration is more important to find any Riemann integral easily?